High temperature hydrogen attack, or HTHA, in carbon and low alloy steels. The goal of the project is to examine the HTHA failure phenomenon, compare prediction models, and provide recommendations to reduce the risk of HTHA. High temperature hydrogen attack is a serious safety hazard encountered in petrochemical and refining applications where high hydrogen partial pressures are present. HTHA failure in a heat exchanger, which killed 7 at the Tesoro Anacortes refinery in 2010, inspired this project. HTHA occurs when hydrogen from the environment diffuses into steel and bonds with carbon atoms in the steel to form methane. The methane reaction leads to surface and internal failures. HTHA risk can be reduced by utilizing accurate models, making appropriate material selections, and following a strict material inspection plan. Discussion of findings. HTHA weakens steel by decarburization or removal of carbon atoms from carbide bonds at the surface. Internally, HTHA weakens steel by decarburization combined with fissuring. Hydrogen diffuses into the steel, forming large methane molecules in voids. These large methane molecules become locked in the steel, unable to diffuse out. The pressure of the methane within the steel forms cavities which become nucleation sites that generate intergranular microfissures that can combine to form visible cracks. Several models for HTHA prediction are examined. The Nelson curves based on empirical data are a traditional model predicting safe zones for operation at given temperature versus hydrogen partial pressure for varying materials. Secondly, a methane pressure model can be used, which utilizes thermodynamic relations to determine the Gibbs free energy, the driving force for methane formation, and the carbon activity within a steel. Thirdly, microstructure characterization techniques can be used which describe the mechanism of failure at the microstructure. HTHA risk can be reduced by selecting steels with more stable alloy carbides which reduce the potential for free carbon in solution and can limit methane formation. HTHA risk can also be reduced by frequent and thorough material inspection. The Nelson curves found in American Petroleum Institute API 941 show that there is a relationship between chrome and molybdenum content and HTHA resistance. Each curve moving upward has greater chrome and moly content. The higher the chrome and moly content within a steel, the greater the resistance to hydrogen attack. Regions under each curve represent the safe zones for operation of temperature versus hydrogen partial pressure. However, failure in the safe regions, like the Tesoro case, have been discovered, and the Nelson curves have been found to be inadequate. A more successful model should be used.